is Tanay from BITS Pilani, Hyderabad, and he will be talking on exceptional topological superconductors and their Floquet analog.
Yeah, thank you very much for this nice introduction, and good afternoon to everyone. I'd like to thank the organizers for giving me this opportunity to present my work here. So I'll be talking about the exceptional topological superconductors and their Floquet analogs. So this part, the first one is basically in equilibrium and the second part is out of equilibrium, but maybe I'll be mostly focusing on the in equilibrium part. And what do I mean by exceptional is essentially the introduction of non-hermiticity. I get some exceptional points. I will discuss all of them. And this work is published in Physical Review B Letters. And I would like to thank Arnab for this nice collaboration, who has done most of it. So then let us, sorry for the interruption. So I'll be discussing what do I mean by higher order topology. For that, I definitely have to introduce what do I mean by topology, and then the non-Hermitian topology, which is an essential ingredient to go into the details. And this part I will be touching upon because it has already been discussed extensively by the first speaker of the day, Noor. And this is the main subject of the paper, so that I will be discussing once the pedagogical introduction is done. So if you have multiple, let's say, if you have multiple potential OL, then that is going to give rise to some kind of band structure in your system, which is something like that, and you have a band gap somewhere here. And in the topological system, what we have essentially is that there is something called band inversion. So some part of the valence band gets transferred into the conduction band, and some part of the conduction band gets transferred into the valence band. And as a result of that, inside this ball gap, you do see some H state. So this is the topology that I will be discussing, and this is something is called as non-adiabatic connections, because you have to drill some hole to get a genus out of to get a donut out of a marble. So this is some kind of non-adiabatic transition which is happening at this place, and this gives rise to topological phase out of the non-topological phase. So this is what it is. Now, it's a simple 1D pedagogical example would be the SSH model. So it's a bipartite lattice system where you have the intra-site hopping V and inter-cell hopping W, and there is a competition between V and W through which you can get a topological phase. For example, if I have V less than W, then if you draw this dx dy on this two-dimensional parameter space, then the closed loop you are getting, that will enclose the origin, and as soon as it encloses the origin, you are going to get a topological phase. So this band gap I am getting here, this is a topological band gap, and as a result of that, you are going to get some H state. So one H state is residing on the very left and the other H state is residing on the very right. So this is what you get. Now going to the topological superconductor, what I have been discussing is on electronic system. If I now introduce superconductivity, then definitely I am going to get topological superconductors. So how do I do? So I introduce some, like it was, the first model was discovered by Alexei Kitaev. It's called POF superconducting chain. So instead of having two bipartite lattice system, I will be having some superconductivity which is living on the bonds. So that is called POF superconductor, and if I decompose my electronic lattice side in terms of A and B Majorana fermions, that I can generate some kind of diagonal hoppings from 2 to 3, which is between blue Majorana to red Majorana, like this, and anti-diagonal something like this. And then in certain limits, if I put W is equal to delta, I can easily figure out that my left side A Majorana is unpaired, while my right side B Majorana is unpaired as well. So this is some kind of topological superconductor model, which is a simple two-band model. So these are all examples of first order topology, but what I will be discussing here is higher order topology. And for that I need to go to a second two-dimensional system. But before that, what I will be discussing here is proximity induced topological superconductivity. And what is that? You do not start with some POF superconductor pairing. Rather, you start with some trivial S-wave pairing, and then you generate POF pairing. And how to do that? Let's start from some parabolic band dispersion here, and then you introduce spin orbit coupling, and that spin orbit coupling will spin split your band, so you get some kind of spin split Fermi surface. So your up band is here and your down band is here, but exactly at k is equal to 0, you get a band degeneracy, and you have to lift that band degeneracy, and for that you need to apply a perpendicular magnetic field, and as a result of that you get a band splitting here, and these are kind of effective, in a sense, these are kind of effective spin polarized band, and between these two parts of the bands you generate an effective POF pairing. and this is called proximity induced topological superconductivity. So the main essence here is that without having p wave superconductivity, you can generate topological superconductivity out of S wave or out of p other than something other than p wave. So this is what I will be discussing. Now again, so topological higher order topological system. So as I was telling you, have to have at least two-dimensional topological system to begin with. Why do we need two-dimensional topological system? Because so that we can reduce the order. As I was telling, the first order topological phase is having, let's say you have a two-dimensional system, then the first order topological phase is having one-dimensional edge modes, boundary modes, and you want to gap out those boundary modes by having certain symmetry breaking mass term. So here I have exemplified one symmetry breaking mass term, and you apply on your system such that you gap out this edge, and this edge, and this edge. But between this subsequent edge, adjacent edges, there is a sign change in the mass term, and that will lead to some kind of corner modes. And once you are getting the corner mode, that is the signature of the higher order topological phase. And so in a very clean way, one can say that any nth order topological phase in D dimension is characterized by existence of D minus n dimensional boundary mode. Let's say if I start from D is equal to 3, which is here, which is a cube, and I want to get the first order topological phase, then definitely I am going to get surface modes, which are all over here. Then for second order topological phase, that means the dimensionality of my boundary modes would be n minus 1, so that should be 2, so D minus 1, so that should be 2, and I am D minus 2, that should be 1, so I am getting one dimensional hinge mode here. So this is the signature of second order topology, n is equal to 2, and for n is equal to 3, so D minus 3 would be 0, so I am going to get the corner modes which are residing exactly on 8 corners of the cube, so these are having 0 dimensionality. So this is how I can reduce the dimensionality of the edge state by introducing certain kind of mass term. So that is the main essence of the higher order topological phase. And now this is some kind of technical details of the higher order topological phase. So I have to begin with some spin orbit coupling with me and some band inversion term with me, and I have to add certain terms such that I can gap out the edge state. So let us do that. So this is the first order topological phase as I was discussing. So you get one dimensional edge mode. And if you solve the problem in semi-infinite geometry, you get band crossing here, and these are your edge modes. Now I have to gap out the edge mode by introducing that higher order mass term. So that is what one can do by adding this extra term. So this is your original Hamiltonian, and if you add this extra term here, then essentially you are gapping out the edge state, and inside the gap, if you now solve the problem under OBC, you are going to get there is some state exactly appearing as a mid-gap state exactly appearing at 0 energy, and if you plot their LDOS, this is what you are going to get. These are all residing on your 4 corners of the sample. So this is what it is. That is how one can engineer the higher order topological phase for the static cases. Now one can also generalize this whole idea to topological superconductivity or proximity induced topological superconductivity. So in case of proximity induced topological superconductivity, you have to start with S wave, and you have to have spin orbit coupling because that will spin split your band, and then you start with S wave, you have to apply some kind of magnetic field to get the corner modes. And if you do not start from S wave, let's say you begin with the P wave, then you have to introduce some kind of D wave form factor to get these higher order modes. So that is kind of a review of the literature. So I will be following this technique where you have some hopping, where you have some SOC. SOC is very much needed because we have to get some kind of topological superconductivity, and for that SOC is a must thing. And then we introduce D wave form factor to get the higher order part, because D wave is nothing but will give you the corner physics at the end of the day. Okay, so this is some kind of another example. So one can have this term, this D wave term, in several ways. One can introduce in the diagonal part of the BDG, and one can also have D wave explicitly present in the off diagonal superconductivity part. But anyway, so these are some details. So now going to this is one part where how we can understand higher order topological superconductivity, let's say. And now I'll be discussing briefly the non-Hermitian aspect of it. So non-hermiticity has been extensively discussed here. So one can engineer non-hermiticity by various means, let's say by having explicit presence of gain and loss term, on-site gain and loss term. One can also have some kind of non-reciprocal hopping. In interacting systems, if you solve the problem, then you get some kind of self-energy corrections, which has an imaginary part that you can think of quasi-particle life, finite quasi-particle lifetime. But this is maybe one of the very closest examples here. So for open quantum system, if you have the Lindbladian, then you have this part here, this jump operator, then you can absorb this part inside your H such that you can write down your redefined Hamiltonian in this manner. And at the end of the day, the first part, the first part of your Leuvennian is given by just like an effective non-Hermitian Hamiltonian. So this is what it is. So you can define the non-Hermitian through the jump operator here for open quantum systems, but these are all microscopic details how you can have non-Hermitian effect in your system. So basically I will be taking a model where I do not care about the microscopic details, rather I just focus on the non-Hermitian term itself. Okay, so if we have non-Hermitian term, let's say somehow, so let's say I begin with this Hamiltonian, and you can clearly see there is H is not equal to H dagger. If I have this term, then I can diagonalize my Hamiltonian, I get these eigenvalues. Definitely these are complex eigenvalues, and these are my eigen energies, and clearly you can see they are no longer orthogonal to each other, and the eigenvalue is definitely complex. Now if I plot as a function of J this eigenvalue, the real part and the imaginary part, I find something very interesting. So if I plot it, then as a function of J, I find a point J is equal to gamma by 4. At this point, the real part is 0 as well as the imaginary part is somehow 0. If I ignore this part, let's say the imaginary part can be 0 as well here. So whenever the real part is 0, it is called PT broken phase, and whenever the imaginary part is 0, it is called PT unbroken phase. Now this model has some kind of PT symmetry. If I ignore this term here, this part here, which can be ignored, I can anyway write down my Hamiltonian in terms of the sigma matrix, and if I put my alpha is equal to 0, then this reduces to a PT symmetric Hamiltonian, and the PT symmetric Hamiltonian can give you real and complex energies as a function of parameter. So these are called exceptional points where your energy is basically you have degenerate energy values. And exactly at this point, something very fancy thing happening on your eigenstate, because if you have this lambda is equal to 0 exactly at this point, and that gives you that automatically tells you your eigenstates, they are no longer you do not have independent eigenstate, rather you have the same eigenstate or they are parallel. So the eigenstate coalesce exactly at this point, which is referred to as the exceptional point. So this is the whole essence of non-Hermitian physics. You get some exceptional point where your band touches as well as your eigenstate coalesce. So these are very interesting physics of non-Hermitian Hamiltonian. Okay, so now if we even complicate our situation, let's say we have a 2 by 2 Hamiltonian, so we can easily write down in terms of d dot sigma. Now if I'm only having the Hermitian part, then the imaginary part of this is 0. So D is decomposed in some real part as well as some imaginary part. Now for the Hermitian case the Di part is 0. As a result of that, I am going to get my energies to be this square, and it tells me that I am only going to have the band degeneracy whenever dx, dy, dz, they all individually vanish. This is going to give me 3 constant for a band touching. Whereas for the non-Hermitian case, I can have di finite, and as a result of that, the complex spectrum is having a modulus term here and some dot product here. So that tells me I am only going to have 2 constants where this modulus they become equal and when they become orthogonal. So only for these 2 constants I have to satisfy in order to get the exceptional points. So the exceptional points are the band degeneracies which are quite abundant, which are very much abundant for the non-Hermitian case. So you are going to encounter an exceptional point if you are dealing with non-Hermitian physics. So this is kind of the diagram for this thing in 2-dimensional parameter space. So this is this di dot dr loop, and you have this real part here. So real part is this loop, and whenever you have the real part crossing the imaginary part, you get the exceptional points, and whenever this part, the real part itself within this window, dr square minus di square. So over this line you get some real Fermi arc. So this is somewhat similar to what the Fermi arc that we see for the real case here. So this is how you can understand the band degeneracies and how it can lead to some topology of your system. Okay, so now another example, like if I have SSH model, then I can introduce non-reciprocal hopping in this manner, which I was telling. So this is your intra-cell cup hopping and this is your inter-cell hopping. And if your M and N, they are no longer 1, in this case, let's say they are 10, 10, then you are going to have this zero energy state. But remember, the zero energy state is no longer located at the very left edge or at the very right edge, rather you see something like this feature. So this is very intriguing situation for the non-Hermitian case that you cannot have if you have hermiticity. Okay, now if you have some competition between M and N, let's say N is higher than M, then N hopping is telling you there is something more flow towards left. As a result of that, you get this left located eigenstates. So remember, these are the eigenstate, these are the states summing over all the eigenstate in the lattice basis. So this is the total structure you are going to get, and this kind of states is referred to as the non-Hermitian skin effect. So this state, and if you go on the other end, when M is higher than N, then definitely this hopping is pushing everything to the right. As a result of that, you are going to get a right located state. So this is called non-Hermitian skin effect. So where your bulk states are also located at your boundaries. So this you cannot have for the Hermitian case. Okay, so having said that, now I can tell what are the questions that I'm going to address in the following time. So the question that I'm going to address is that can I generate some exceptional higher order topological superconductor phase? So that means the Hermitian limit is trivial. If I add, or the Hermitian limit is somehow there, but if I add non-hermiticity, can I have the higher order topological phase out of due to non-hermiticity? In other words, can I extend the topological boundaries if I add the non-Hermitian terms? So this is what the main question is that I will be asking. So definitely it is based on other than p wave pairing. So I have proximity induced superconductivity, and here I have d wave pairing with me. And then once I have this kind of extension of phase boundary, can I characterize the phase or whatever phase I am getting by some topological invariant? That is the second question, because whenever I am telling about some topological phase, I have to have a topological invariant, and that is I'll be addressing here. And then last part is that, okay, so everything I'll be talking here is about the Majorana zero modes or zero energy physics. Can I generate some anomalous mode which are having finite energy if I use Floquet drive? So these are the three sets of questions that I'm going to address. Now again, so the model we will be having in our mind that should have hopping. So this is kind of the hopping term, and again if I combine with the on-site mass term, this whole term is giving rise to some kind of first order topological physics, I mean in a sense crudely. And these are your spin orbit coupling term here, and then I have delta, which is d wave. So this is my d wave form factor. So I will be mostly talking about the second order topological phase, so I forget about this thing for the time being. So this is kind of the underlying model that I am having in my mind. Now I have to introduce the non-hermiticity in the model. So what do? I introduce the non-hermiticity in this part, in the diagonal part. So this is written in the BDG basis. So I have particle hole and I have other degrees of freedom, which is sublattice and spin. So as a result of that, the diagonal part here I am introducing the non-hermiticity, and that I introduce in terms of this gamma x and gamma y. So this is sin kx plus gamma x and sin ky plus gamma y. So this can be thought of like some imaginary Zeeman field for simplicity. So this I am adding to my diagonal part of my BDG Hamiltonian, and then once I add this thing, so then the symmetry class of the model changes, because you no longer have the Hermitian counterpart, rather you have the non-Hermitian part, and as a result of that, H dagger not equals to H. As a result of that, you have some ramified symmetries or some kind of redefined symmetries. So you get two flavors of particle hole, two flavors of time reversal symmetries, because of the fact that H dagger is not equals to H. So the symmetries that this model respects is this ramified time reversal symmetries, and the operators are here. Remember here the U operator for this non-Hermitian case, U becomes unitary, and the particle hole dagger symmetry that the model respects, it is also unitary. Whereas if you get rid of this gamma x and gamma y term, then usually in the Hermitian case your particle hole and time reversal symmetry, they are both anti-unitary, which is here, non-unitary, which is here. So this is what it is. And now behind this kind of particle hole and time reversal symmetry, this model has other crystalline symmetries, because what I'm going to have is this corner mode, and in order to have those corner modes, I have to maintain certain kind of crystalline symmetry in order to get those corner modes. And this model, the Hermitian model, is preserving this mx, my and C4, whereas the non-Hermitian model does not preserve anything of this above 4 symmetry. So it breaks this 4 symmetry, but very interestingly, the non-Hermitian model preserves mxy symmetry, mxy bar symmetry, and the chiral symmetry. So these are very important for the non-Hermitian model, this mxy bar and chiral symmetry. So this will determine the localization property of my corner modes later on. Okay, so now again I have to check my energy spectrum, and my energy spectrum is complex. So I have drawn here the real part, imaginary part, and the mod E part. So the first line here that is plotted, which is for periodic boundary condition, and the second line is for open boundary condition, just focused on this part, let's say. So we have real part of energy, which is drawn for periodic case. You will see some degeneracies appearing here in the real part. So those are lined up, those are kind of a continuous array of line you are getting here and here, and those are symmetrically placed around -2 and +2, and these are the points above which you do not see those degeneracies. So these are the black lines are the points above which you do not see those degeneracies, and within this window, which is covered with this yellow color, that is why, and you are going to see these degeneracies. So these are kind of you are getting from your bulk band structure, and if I solve the problem, if I solve the problem in momentum space, then this is what I am going to get, this structure, this relationship, and you have S plus minus. So if I put S is equal to, remember here Tx is equal to Ty is equal to 1, gamma x is equal to, for this case gamma x is equal to gamma y. So if I do that, then I am going to get symmetrically around ±2 some points, and that window is given by this root over of 2 gamma square. So this is that window, root over of 2 gamma square here, and it is -2. So from this I am getting ±2, and from this I am getting this yellow window. So this is what I get. Now this picture is telling me, okay, there cannot be any edge mode within this window. Definitely there can be edge mode here, or there can be edge mode here, but this window is kind of trivial. So I'm only supposed to get the edge modes within this region. But now if I solve the problem in open boundary condition, I get something extremely non-trivial. So I see under open boundary condition, I am going to get boundary modes for here. These are all corner modes. These are exactly going beyond this black line here. So it crosses the black line here and it goes till this red line, and same for the right hand side. So this tells me there is some kind of bulk boundary breaking, bulk boundary correspondence is somehow broken. So I'm supposed to get the edge modes only within this window, but I'm not getting that. I'm getting the edge modes here, the boundary modes here, but not only within this window, the boundary modes extends beyond this window, till this red point. So there is some kind of bulk boundary correspondence breaking is going on. Now I have to resolve that breaking. So that is the essence of non-Hermitian effect in this Hamiltonian. Okay, so how to understand that? Because we start with some band structure, then if I increase my system size, bands gets denser, and if I introduce non-hermeticity, this kind of is going to give rise to some kind of continuous band structure, and that can be understood by some modification in your momentum. So that is something called non-block momentum. So if you introduce the non-block form of your momentum in certain way, then you can probably understand the breaking of the bulk boundary correspondence, and you can retrieve the bulk boundary correspondence. So this is the problematic zone. And this is the problematic zone. So from red line to this line. Now if I have this kind of block momentum with me, so K is now becoming K prime plus I beta, where beta is given by gamma by lambda. So this of this form, then if I plug into my bulk Hamiltonian, then what do I see is that I can match the open boundary condition phase diagram. So this is the phase diagram in gamma versus M plane. So what I was getting initially is this line. Now if I introduce this non-block form, then my momentum, my topological mass is going to change as a result of this thing, this non-block form of the momentum, and I get new topological mass term, which is this thing, and which then exactly clarifies the boundary. So this is what is the boundary which I am getting from the open boundary condition, and I can now again relate it to the bulk boundary correspondence. So this is the topological window, m less than 2 plus gamma square, and this is the non-topological window, whereas these yellow lines are those bulk lines, those are not giving me the right bulk boundary correspondence. So I can now, if I non-block, if I have introduce the non-block form of the momentum, I can get this thing. Now what does this give? Additionally, it gives initially you have m0 is equal to 2, that was your topological phase boundary. Now it is increased by gamma square. So that is the additional part. If you draw a vertical line here, so this additional part you are getting, and that is induced by the non-hermiticity of your Hamiltonian. So this additional part was not there in the Hermitian case. If you put gamma is equal to 0, it is simply 2, and this additional part you are getting only because of the non-hermiticity of the problem. Okay, so now you can have another consequences of bulk boundary, another consequence of this kind of non-block form, which I already told, which is referred to as the skin effect, because your momentum is modified with a complex number, and if you have block functions with you e to the power ik, and if I become complex, you will get some localized nature. And as a result of that, your bulk modes, which are localized, which are this deep inside your mid gas spectrum, whatever, this deep inside your spectrum, so these modes are going to be localized on your boundaries as well. So this is what we are getting. So this is a bulk mode, the insets are giving you the bulk modes which are here, and these are also localized on your corners. So this is called skin effect, and that we have also seen here. And we have also studied this thing against the disorder. So we introduce some kind of mirror symmetry preserving disorder. So that is the modes that we are getting. This is also stable against the disorder. So this this phase is not fragile. It can withstand disorder as well. So now, if I detune from the symmetry, detune myself from the symmetry, and I somehow get rid of this mxy symmetry or mxy bar symmetry, then what will happen to my corner mode? So I am having only one corner mode, as you can clearly see it here. Now I can change their location depending upon the sign of my gamma x and gamma y term. For example, if they are both positive, I was having them here, gamma x equal to gamma y. Now if I change their sign, then I can change their position as well. For example, it is plus and minus, I am here. If it is minus and minus, I am here. If it is minus minus, I am here. If they are no longer equal, mod value is not equal, and they are no longer equal, definitely there I am breaking this mxy symmetries or mxy bar symmetries. As a result of that, they are no longer located on a single corner, rather they are located on two corners. So this is the role of the symmetry here. If I get rid of the symmetries by having different values of gamma, I can change their localization property as well. And that is the another kind of strong nature of your non-Hermitian term. Okay, so then this is something you can also engineer all of these features by having a S-wave superconductor. So what we have been discussing so far is D-wave, but you can also have, without having D-wave, you can also have S-wave with you, and that can give you the same physics. So that I am not going to discuss, but I can briefly tell you like how do I characterize this kind of phases. So far I have been discussing you can get these topological phase boundaries by the non-block form, and that is due to the non-hermiticity. But how to characterize this whole topological region, because I am giving some value here 0.5, which is nothing but something called bi-orthogonalized nested polarization. And this is something like for the first order case, we all know that if you have polarization like Berry phase, which is essentially the marker of your topological property, you can derive the Berry phase in terms of your polarization, which is nothing but the sum of your one-year centers over the occupied bands. So this is the first order polarization, but remember here what we are dealing with is second order phase. So the first order polarization is not going to work here. So for the second order case, we have to follow a certain trick, like this is the roadmap for that. So first we have to get the position operator in the occupied space. We get the first order polarization, then we look for the position operator onto the first order one-year band. So one-year bands are something that we get from here. So next we look for the position operator project the position operator associated with the projected on the subspace associated with the first order one-year band, and that one-year band we get from here. and that will give us the second order polarization. And again, so this is all technical details, so we will be having this quantity with us to characterize the topological phase, and the first order quantities and the first order topological polarizations is 0 or is completely gapped out. So this is what we have observed. You have to do the bi-orthogonalization version of it, so this technical details. So if we do that, the first order polarization have to be gapped out, so this is what we draw. So for the Hermitian case, since the gamma x and gamma y, they are no longer there, so I am having all the symmetries with me, mx and my, all the symmetries with me, and you can clearly see the symmetric nature of them. So gamma x and gamma y, they are symmetrically gapped out, and this is their mode value, and they are falling on top of each other. So this is nu x and nu y for the Hermitian case. But for the non-Hermitian case, that symmetry is broken because you have finite gamma x and gamma y. You have broken mx and my symmetry. As a result of that, they are no longer symmetric, and if I plot the mode value, they are not falling on top of each other. So this is what it is. You can break the gap structure of the underlying topological invariant as well. Okay, so now maybe in last 5 minutes what I can discuss, everything what I have discussed so far is basically on the zero energy physics of the model, but can I have finite energy edge state or boundary modes? So for that I have to introduce Floquet, and which was already extensively discussed in the first talk. So it will give rise to some kind of band crossing between the Floquet-Brillouin zone. So here your energy is no longer defined on one-dimensional momentum space, rather the energy is defined on two-dimensional torus, where one dimension is given by the momentum and the other direction is given by the frequency. So as a result of that, you are going to get some frequency space Floquet-Brillouin zone, and if you have intersection between the Floquet-Brillouin zone, that will give rise to some kind of finite energy boundary modes which are here. So can I have finite energy boundary modes by introducing Floquet dynamics? And the answer is yes. So we drive the mass term in periodic kick-like manner, and we start from trivial phase. So this phase is trivial such that m naught is greater than the topological phase boundary, so it is beyond that boundary. So we start from trivial phase and then we introduce this mass term in kick-like manner, and at the end of the day we do some analytics and we see that the effective Hamiltonian is having some modified mass term, and that modified mass term is having the non-Hermitian term in them as well as the driving term in it. So you have this additional term. So that means the topological phase boundary is also modified with your driving. So this is all high frequency drive, and then we plot it. So okay, so this is the line for Floquet higher order topological phase, and this is the boundary. So this is topological and this is trivial, and this green line is given by this equation, which exactly matches with our numerics for high frequency drive. Now one can also have, so again this is for the zero energy case, and as I was telling, the aim here is to engineer pi modes, which are the anomalous mode here. So that we have also shown, if we reduce the frequency, one can also generate these pi modes here. And the pi modes are located somewhere here in the one corner. So this is how you can engineer zero mode and pi mode, and if you tune your frequencies, you get a whole zoo of phases, like not phases with different numbers, so you can tune the numbers of the corner modes. So here you can have 8 corner modes, here you can have 32 corner modes, like that. So it's a whole range of frequencies that you can vary to get different numbers of the corner modes. Okay, so with that I can conclude. So what do I get here? So I started from some trivial model, and I want to induce topological superconductivity by non-hermiticity. So I do that. I considered the underlying building blocks is definitely the Hamiltonian that I was considering is definitely having SOC, hopping first order mass term or something like that, and the SOC is very much important. So that I have started with. I introduced the d wave superconductivity, and I introduced some kind of imaginary or like imaginary magnetic field, and that would lead to the higher order exceptional topological superconductor phase, because it is 2 plus gamma square. In the Hermitian case you only get 2, so phase is bounded between plus minus 2, but in this case it is plus minus 2 plus gamma square, something like that. And in order to understand that phase boundary, you have to go back to the non-block momentum, and as a result of that you get some skin mode, and the non-block momentum is also important in order to understand the topological marker of the problem. So that we did, and we define the topological phase with that marker and in the bi-orthogonalized version of it. And at the end, we also simulated the Floquet anomalous pi mode. So this is what it is. And so there are some experimental evidence which has been shown for the non-Hermitian case as well, where you can somehow reduce the finite size effect by introducing non-hermiticity. So this is a very recent experiment published in PRL, where they have shown that if you have finite size effect, so this topological phase boundary is somehow detuned, and now if you introduce some kind of gain and loss term in the waveguide, you again the topological phase, you regain the topological phase boundary in the thermodynamic limit. So this is what it is. So this is also important that in the optical or like acoustic system, you can introduce this kind of gain and loss term by a certain manner. So, and the Floquet dynamics can also be experimentally like kind of implemented in some metamaterial aspect, as far as I know. I mean, in most of the cases it is metamaterial. So here one example from acoustic system where you can array, you have some array of your waveguides, something like that, and so to mimic the Floquet kind of picture, so Floquet drive, and you can also engineer the corner modes here. Okay, so with that, I'd like to thank all of you for your attention.
Thank you, Tanay, for a nice talk. Time for questions.
Hello. Yeah, you talked about the three symmetries in the non-Hermitian setting, right? And you said that all of them admit unitary representations?
Yeah, because of the fact that because of the fact that you have h dagger not equals to h, and that gives you another degrees of freedom here. So you can define your non-unitary symmetries in two flavors, one with h star and another with ht, and that makes you this u unitary and this uc unitary. Whereas in the Hermitian case, the Hamiltonian always have h is equal to h dagger, so you are no longer left with any as such two flavor of choices.
So if you have all unitary symmetries here, why do you need to distinguish between them?
No, because at the end of the day, so this is, you do not have 10 classes, 10-fold classification here. You have 38-fold classification here. So you have to distinguish among all these classes. So this falls under one class definitely, which I do not know at the moment. But this all classification tables is based on these ramified symmetries now.
Okay, and also when you have multiple corner modes in the very end of your talk, like 16, 32.
Right.
So do these modes occupy various Wyckoff centers of the unit cell?
Not really actually. So in the unit cell, whatever the nested polarization we are computing, that tells you the value is half quantized. So that tells you the 1 year center is actually halfway located between your lattice sites. As far as I know, all of them should be located on the same site. If you are referring to the Wyckoff position same as the 1 year center, I do not know. If they are same, then as far as I know, the 1 year centers for this case, for the higher order case, you have the, they are all always halfway located from your lattice sites. So this is the signature of the higher order phase.
And they are slightly at different energies, right? For these additional
not
corner
really.
modes?
They are all degenerate at zero energy or whatever at pi energy. So they are all sitting at the same energy.
Okay.
If not, then let's thank the speaker once again for a nice talk.